In this video, I'm going to be talking about how to solve a Coulomb's law problem. So let's talk about the basics of Coulomb's law, what all the variables are, and how to plug them into our calculator properly. So in order to solve any Coulomb's law problem, the electrostatic force is equal to the constant K times Q1 times Q2, which is the first and second charge, divided by r squared, and r is the separation distance. So sometimes you'll see that written as F equals K Q1 Q2 over D squared. Okay, so either way, the r or the D are talking about the separation distance between the two charges. So in this tutorial, we'll be just discussing cases where there's just two charged objects, and nothing weird with like angles or multiple charges involved. All right, so our K value is going to be a constant, which is 9 times 10 to the 9th power. We're going to have two charges that are going to be measured in coulombs. We're going to have a separation distance measured in meters, and then we're going to have a force measured in newtons. So what I've decided to show you is two variations of Coulomb's law type problems without just solving for the force, because solving for the force is the easiest variation because all these values are on the same side and you don't have to really do any algebra, or there's nothing too tricky about it. All right, so in order to do these correctly, you're gonna have to make sure you plug them into your calculator, which for a lot of things, plugging things into your calculator is pretty simple. When you're plugging in a bunch of extremely small or large numbers with exponents, it can get a little tricky. So what I'm gonna do is set up this first one. It says a proton and an electron have an electrostatic force of 5.76 times 10 to the negative 29th newtons. And these are just known values as well. This is 1.6 times 10 to the negative 19th coulombs, and then an electron has the same charge. It's just negative 1.6 times 10 to the negative 19th coulombs. Okay, so remember this negative over here doesn't mean that's a negative value. That just means I'm sliding the decimal 19 places to the left. It just means it's an extremely small number. Okay, so only the negatives in front here will tell you that's an actual negative number. Okay, and it says, what is their separation distance? Okay, so if we go ahead and set this up into Coulomb's law, it's going to look something like this. All right, so I have everything all set up. I place everything where it needs to be. And like I said, it can be a little tricky plugging some of these numbers into your calculator. So I will give you some tips on how to do that properly so that your calculator understands what you want multiplied and divided in the problem. All right, so for this particular problem, I already know that I'm going to eventually take the square root of a value so that I can just find regular r, my separation distance. So I don't necessarily need this negative in here, and I can already tell that I'm going to end up with a negative number. And you can't take a square root of a negative number. So should you plug in the negative? I guess it kind of depends on your preference. I would say you could or could not leave it in depending on the problem, but I definitely don't want it because I can't take a square root of a negative number. Okay, so the point of having a positive and negative Q value would be knowing that they attract. So then this proton would have a force pulling it this way, and this electron would have a force pulling it that way, which would be an equal and opposite to each other. Okay, so with that being said, I will just make this negative a positive. So what I'm going to do is, this is the way that I would plug it in. I would take all of the values in the numerator, plug them into my calculator, and then press enter. The way that I would do that is I would either plug them in like 9 times 10 to the 9th power, or the second way you could do it is you could hit 9 hit the double E function, and then 9 again. Okay, when you press that into your calculator, it will look like this. Okay, that double E function in your calculator means times 10 to the blank power. Okay, I just like using that because it's a little bit quicker and easier. It really doesn't make a difference whether you want to plug this in or plug this in. Okay, so when you hit 9, double E 9, it will look like this in your calculator. This means 9 times 10 to the ninth power, which is obviously the same as this number right here. Okay, you notice that I wrap everything in parentheses because there's a bunch of numbers here, but it's only representing a single very large number. And there's a bunch of numbers here that's just representing a single very small number. So I'm going to use a ton of parentheses to make sure my calculator knows that these are single numbers, and it's not a bunch of different numbers. I mean, it is kind of a bunch of different numbers, but like I said, it's representing one value. Okay, so I'm going to plug in my really large or small number either this way or this way, depending on your preference. I'm going to wrap it in parentheses, all three of them, press enter, and then I'm going to get 2.304 times 10 to the negative 28th. Okay, from there, basically, I have to do is two steps, which I would just cross multiply these two numbers so that the r squared pops up over here, and it's for the most part isolated now. And then the 5.76 times 10 to the negative 29th drops down there. And then you can square root your values from there. So if you have r squared equals 2.304 times 10 to the negative 28th divided by 5.76 times 10 to the negative 29th. Okay, you can go ahead and divide those, and then you would square root both sides, and then you're done. And then your R would come out to a nice even 2 meters, which is typically not the case. It won't come out to a nice clean number like that all the time. Okay, so just to recap, you definitely want to make sure you're very careful about plugging the numbers in, putting a bunch of parentheses in there. I decided to cross multiply these. If you wanted to say you want to multiply both sides by r squared, then r squared would cancel here and then show up over here. And then you would divide both sides by this number. Either way, this would drop down here, r squared would pop up over there. And then you get your separation distance of 2 meters. All right, now for our second variation of Coulomb's law that's a little bit more complicated is it says two equally charged balloons are repelling one another with a force of 3 times 10 to the negative 25th newtons. Determine the charge of the balloons if they are separated by 0.5 meters. So let's go ahead and plug those values in. All right, so I left it like that because my Q1 and my Q2 are my unknown values. So it says two equally charged balloons. So that means that the Q1 and Q2 are the same. Okay, so if you have two values that are same, well, they just happen to be unknown. So like say, for example, if you had an x times x, that's x squared. So instead of x, I'm just going to make it q squared. Okay, so sometimes people would put 2q as opposed to q squared, but again, you're multiplying the two, so it would be a squared value. To keep it short, you'd basically multiply both sides by 0.5 squared. And again, I'll look at it in terms of cross multiplication, which would be multiplying the force of 3 times 10 to the negative 25th times 0.5 squared, and then dividing it by this number, 9 times 10 to the ninth. So dividing both sides by that number, and then eventually ending up by square rooting that value. So it is a 3-step process where you would multiply both sides by this, and then this times this is your first value, and then enter, and then divide it by 9 times 10 to the ninth, your k value, which is basically cross multiplying it down and over. And then you would finish off by square rooting it, and then your final q value would be 2.89 times 10 to the negative 18th coulombs. All right, so like I said, I didn't show you the easiest variation of Coulomb's law, which is finding the force, because that would just be multiplying k times q1 times q2 and dividing it by r squared. If you were to do that, my recommendation would be to multiply everything in the numerator, press enter, and then divide it by the separation distance squared. And remember to put that in parentheses. You press enter, you should get the correct force. So when plugging these numbers in, making sure you're very careful about plugging things into the calculator and getting your exponents in there is one of the keys that's a little bit tricky at first. Then you get the hang of it. Then it's just kind of working the numbers around in order to find your solution, whatever that may be. We're going to be talking about Coulomb's law with multiple charges. So we're going to have a one-dimensional problem with 3 charges that are in a row, and how to find the net force acting on a single charge. And then we're also going to do a more complex version with charges in 2 dimensions with forces that are on angles. So for these types of problems, I assume that you're already okay with a straight plug-in type problem to find the electrostatic repulsion or attraction by putting in the k value, the 2 charges, and then the separation distance squared. Okay, one of the keys to doing these types of things is making sure you plug it into the calculator correctly. So you want to make sure you put all of these numbers that are in scientific notation in very carefully, and then always wrap them in parentheses so that your calculator is aware that that's one really large number or a really small number. So if we're taking a look at a problem like this, and you're asked, what is the net force on Q2? Chances are you're going to get the values for Q1, Q2, and Q3 with some separation distances. Okay, so for this first part of the video, I'm just going to talk about conceptually what you would do. And then when I do the more complex version over here, I'll actually plug in all the number values and then work that out a little bit more thoroughly. So for this particular one, let's pretend that our Q2 has a positive charge. Let's pretend that our Q3 has a negative charge. And then let's say our Q1 has a positive charge as well. Okay, what you would do in this case is you would figure out the force between just Q1 and Q2 using Coulomb's law. And we know that's going to be a force of repulsion because they're both positive. So then this force would be pushing towards the right. So that we'll just call that force of Q1 on Q2. Okay, and then for the force of Q3 on Q2, same thing. You would plug it into Coulomb's law with the K value, the 2 Q values, and then you're also going to put in the new separation distance. And because these are opposite charges and it's a force of attraction, this one is also going to cause a force to the right. So this is the force from Q3. Okay, so essentially all you're really going to do is you're going to do Coulomb's law twice, and then you're going to add them together. Okay, for other scenarios, you may subtract them. So say, for example, this force over here was negative, and then you still had the negative charge, and then you have a positive charge in the middle, and then you had a negative charge over here. Both of them are going to attract this charge that's in the middle. So they're basically both trying to attract it, and they're tugging it in 2 different directions. In that case, you would just subtract the 2 forces for your net force. And then obviously, whichever one has the greater force, the object is going to get pulled and accelerate into that particular direction. Okay, so that's how you solve a Coulomb's law problem with multiple charges in 1 dimension. So getting to the second part over here, it's much more complex. So the problem I'm going to solve is basically what is the net force on Q1? Okay, so what I'm going to do for that is I have some numbers for me. I have the 2 meter separation distance between Q1 and Q2, and then between Q2 and Q3, and then I have a couple different charges here. So what I'm going to do is I'm going to make sure I find the force between them and plug in the proper charges for my Q1 and Q2, and then the correct separation distance as well.
Avant, tu voyais que de la merde. Maintenant, au moins, tu vois plus rien.
All right, so I finished solving for the amount of force that Q2 applies on Q1 and how much Q3 applies on Q1 as well. This one was a little bit more simple because I already have the separation distance of 2. And then I do have a positive and a negative number here, so technically the force comes out to be negative. All I'm really telling myself is that I know this is negative and this is positive, therefore Q1 is going to be attracted towards Q2. Okay. Other than that, I don't really care too much about plugging the negative in there. You could or could not add that negative in there. For this second problem, we have our two Q values. We have 8 times 10 to the negative fifth, and we have 7 times 10 to the negative fifth, but we don't actually have our separation distance given to us directly. But this is 2 meters away and this is 2 meters away. So it's basically two parts of a triangle. And then this would sort of be like the hypotenuse. So you could use Pythagorean theorem. You could say that this is a isosceles triangle or where there's two 45-degree angles. So this should be 2 root 2. Whichever way you want to go with it, 2 root 2 probably would have been a little bit more exact, but I just went with 2.83. Okay, so I have 2.83 meters as my separation distance because that's the hypotenuse of this triangle. Okay, so that was actually the easy part of this problem. And then it gets actually a little bit more complex from there. So now that we have all of our numbers, we have Q2 acting on Q1, and what it does is it pulls it down. Okay, I know it pulls it down because this is positive and this is negative, and then opposites attract. So it's pulling it down with 7.88 newtons of force. Okay, and this is where it gets a little bit more complicated. And then between Q1 and Q3, these are both positive numbers. So I know it's going to be a force of repulsion. So it's going to push it away. And we know that the force it's pushing away is 6.29 newtons. Okay, now just as you've done probably before with velocities or other different forces, anytime you have something on an angle, you have to break it up into components so that you have a directly horizontal component and a directly vertical component. So this one is actually going to be no different. And what I'm going to do is I'm going to take this 6.29 newtons and use it as my hypotenuse. And I'm going to create a horizontal and vertical component. Okay, this angle over here is going to be 45 degrees. And then if I use sine and cosine, we can find our different components of the triangle. So I'm going to use sine to find this opposite end. I'm going to use cosine to find the adjacent end. And I've already worked that out a little bit earlier. And because it's a 45-degree angle, it works out sort of nicely because both of these values are going to end up being the same.
Avant, tu voyais que de la merde. Maintenant, au moins, tu vois plus rien.
All right, so now my focus is just taking a look at all of my components that are perfectly horizontal and perfectly vertical from one another. So what I'm going to do is I have two vertical components. I have 4.45 newtons up and 7.88 newtons down. So I'm going to subtract those because those are in opposite directions. And then that's going to leave me with 3.43 newtons downward. Okay, so again, I have 4.45 newtons up and then 7.88 down. They're in exact opposite directions, so I'm going to subtract them, and I have an additional 3.43 newtons down. Okay, we have no horizontal forces besides this 4.45 newtons, so I'm going to use my tip to tail method, add my vectors, and I still have this 4.45 newtons over here. Okay, so for my final answer, actually what I'm going to do is take the resultant of those final components. Okay, I can use Pythagorean theorem one more time. A squared plus b squared equals c squared, or I could use a trig function if I'd like, and it's going to come out to 5.62 newtons. Okay, and that's going to be my final answer. Okay, if you wanted to solve for the angle at which it's pointing, if you want to solve for this theta right here, you can use an inverse trig function. So say, for example, if you use the inverse of tangent, okay, tangent is opposite over adjacent. Okay, pop that in my calculator, and then theta comes out to 52.38 degrees. Okay, so there is a lot of work on the screen here. So let me just sum it up and then walk through the steps one more time. Okay, so basically what you want to do is your first step is always to start out with Coulomb's law. Just find the force between the two charges that you're currently looking at. So there's a Q1 and a Q2 because you're only going to analyze two charges at a time. So it might be these two first, it might be these two first, but you only analyze two at a time. Okay, you make sure you plug in the proper Q values, make sure you're taking a look at the correct separation distance, plug it in carefully with a lot of parentheses as shown over here, and then you have your forces. Once you get your forces, you're going to add or subtract them based on the way that they're pointing. So the key is to make sure you draw a lot of pictures, to draw all your vectors so you can see which way they're pointing. You can clearly see this one is going up and this one's going down, so it would totally make sense to subtract them. And we have that additional force going downwards. And we were still left with that horizontal piece over here, 4.45 newtons to the side. Okay, so the result would be, as this is pulled downward pretty strongly and pushed over diagonally with a little bit less force, it's going to cause the charge to go down and to the left at a 52.38 degree angle with 5.62 newtons of force. Thank you for watching and listening.